Alright, let's pick back up where we left off. We were talking about fancy pointer stuff, smart pointers. So we just got finished talking about unique pointers, which is a nice thing that you can use if you only ever want to have one pointer guaranteed into the heap to a specific place. And that is sometimes necessary because you don't trust yourself or other programmers. Unique pointers are nice. The next one that I want to talk about is shared pointer, and this is the one that you'll most likely use the most often. It gives you the best of most of the worlds. So a shared pointer of some type t, it wraps around a t on the heap as usual, except you can copy it. So you can make a shared pointer, maybe we can call it sp, and inside of it has a real pointer to the heap, and you can actually have multiple pointers there. So we got our sp1, it's got a pointer into the heap where I'm storing my 42, and you can actually copy construct or copy assign another pointer that points to the same spot. So you can share the fact that both of these are pointing to the same place. Okay, so that is shared pointer, and make shared of t works exactly as you would expect. It just calls the constructor on the object that you're creating on the heap for yourself. But the issue arises when, okay, now I have two pointers to this thing. C++ is supposed to delete this for me. How does it know when to? And the idea is it keeps what's known as a reference count. So there's a second field that points to another heap object that is known as the reference count for this thing. This is the reference count. And what that does is it keeps track of how many pointers exist to this heap address. Okay? Which is very odd, but it's going to work. So it just keeps track of how many shared pointers are still alive and pointing to that object. So if sp1 is pointing to this 42 thing, and sp2 is also pointing to 42 on the heap because we assigned like sp2 equals sp1 or something, that would bump up the reference count from 1 to 2. And so now C++ knows, as it's running, that there's two things pointing to this. And eventually, once these go away, like they hit their closing braces, and they go away, like now the reference count goes down. And eventually, the reference count goes down to 0, at which point we can finally delete the original thing and the heap reference count that it was keeping track of. Okay? So eventually you can do all of that. I don't know the best way to like do all of this. Maybe I'll keep all of this stuff and I'll just write x's. That'll work. Okay, so that is shared pointers in a nutshell. They are essentially pointers. You should consider using these for the rest of your life. So let me make a, gotta include memory, of course. And I don't know, let's do strings instead of ints this time. So I can say make shared of type string. I'm going to make a string on the heap, and I'll call it, I don't know, sp, because it's a shared point. Oh, I'm sorry. It's a shared pointer to a string. I'm getting ahead of myself. Called sp equals make shared. And this is what's going to call the constructor with, I don't know, hi mom or something. So now that exists on the heap, and this is sp1, let's say. And then, I don't know, just to make our lives more interesting, let's have a function that returns a shared pointer. Called makeStringOnHeap, and that will actually do this. Okay, so I've got sp1, I can return it, and then down here in main I can make sp2, and set that equal to what I get back from makeStringOnHeap. And then I can make sp3 that points to sp2 by saying, that points to the same place that sp2 is pointing, by saying equals sp2. And now I can go and change the string. I don't know, I can double it or put an exclamation point at the end of it. And then I can print out sp3 because they're pointing to the same place. So isn't that all beautiful? And nowhere did I say new, nowhere did I say delete. Right here I said make shared. That's bringing it all together. Okay? That's the idea. Okay. So, let's give it a try. And voila, did I put an exclamation point at the end of this string that I made on the heap up here. So originally, let me walk you through this code. It's a bit odd how it's working. But it's beautiful nonetheless. So I have attempted to copy that. Let's make sure this is still going, yes. What I've done is originally I made sp1 up here in this function, and so I made it. Here's sp1. It's pointing onto the heap with holding hi mom. This is the heap, and this is the stack for multiple functions. And then there's also a heap variable that keeps track of the reference count. And so there's one thing pointing to hi mom right now. It's just sp1. And then this function returns to main on line 12, and sp2 gets the value of sp1, so it points to the same place. So for a split second, we've got sp2 pointing to the same place that sp1 does, and the reference count is 2, but then sp1 goes away. So then this goes away, this goes back down to 1, and now we're on this line. sp3 equals sp2. Then sp3 is going to point to the same spot as sp2, but I should make it over here. Whee! It points to hi mom again, and then the reference count, because it knows where that lives as well, it gets bumped up again, because now I have 2 live things pointing to this place in memory. Okay? Very weird. Then I can actually use the pointer to add an exclamation point, and then I can use the other version of the pointer. Like I use sp2 to add the exclamation point, but I can use sp3 to go and print the thing out. Why not? And so that line does that. And yeah, after main is finished, these all go away now. And then the reference count gets bumped down from 1 to 0, and then the rest of this all goes away. And we are left with a perfectly pristine heap at no expense to us. We didn't have to waste any thought worrying about that. So that is shared pointers in a nutshell. And gosh, are they beautiful. So that's very nice. And most of the time, you're going to use shared pointer, except when you need to use weak pointer. Okay? So sometimes you have a pointer, and it already exists, like you have a shared pointer in specific, and you don't want to add to its reference count. So this is, I should just be explicit. Sometimes you have a shared pointer that already exists, and you don't want to add to its reference count. So maybe you know that what you're pointing to is not going to be deleted, so you don't have to worry about updating its reference count, which I guess technically takes some amount of constant time. Or maybe using a shared pointer is going to mess up the deallocation process, and I'm going to show you that example. So that's when you use weak pointer. So it's a shared pointer, but it doesn't add to the reference count. Okay? Dun dun dun. So that's what a shared pointer does. Sorry, that's what a weak pointer is for. So it just weakly points to this thing. So I can have a shared pointer that points to my 42 on the heap, and it has, I'm drawing it like a tree node, and it has its reference count of 1, and then I can have a weak pointer that points to this place, but does nothing with this reference count, keeps it at 1, even though there's another thing pointing to it. So technically, if the shared pointer was going to go away, if it did go away, we would suddenly have deleted this memory, and we shouldn't be accessing it through the weak pointer. But when we use a weak pointer, we assume that that's never going to happen, okay? So we assume that we'll be able to access the pointer. We'd like to have it like that. So weak pointer looks like this. And in fact, it knows better. So you should always check this. If the shared pointer that it belongs to went away, the weak pointer is expired, and it knows that it's expired. Okay, it'll return a Boolean whether or not it has been deleted. So that's useful. So instead of saying this, maybe I should say, if you're ever doubtful about whether or not you have a shared pointer to point to, use .expired to check. Okay, that'll check whether or not the weak pointer is okay to use still. Okay, whether it points to something that has not yet been deleted. That's a weak pointer. So the idea is a weak pointer holds the same address as what a shared pointer does, which means that you cannot do make weak or anything like that, because you have to give it a shared pointer that already exists. So let's see how C++ makes that happen. Well, you have to give it a, let's see, I guess technically you can copy from other weak pointers, but the original pointer needs to be a shared pointer somewhere down the line. And so if you need to do operator equals, eventually you'll be giving it a shared pointer somehow. Okay, that's the idea. So yeah, I think that's all I wanted to say about that. I think we can give an example now of the issue. So this is the issue I'm about to show you is a circular linked list, and we can use linked lists with shared pointers. Like we can use these fancy smart pointers to handle erasing the memory for us. So I can make 1 arrow 2 arrow 3 where these are shared pointers. Okay, and this is null, and the second I'm done with like the head, then or the first pointer, that's like a shared pointer as well. Boop. The second I'm done with that, then the whole list will delete itself. Isn't that beautiful? Because it's like, okay, one person's pointing to me here, but then it will realize, okay, first is now gone. So delete first, the thing it's pointing to, delete itself, delete itself, delete itself. It'll delete itself forever, which is super nice. If you use shared pointers, the list will correctly become deleted. The issue arises if you ever use shared pointers for a circular linked list. So let me draw it out very specifically now. With the little syntax that I've been building up, the little diagrams that I've been talking about. So let's assume we have shared pointers. We have a pointer to the first node of the list. It looks like this. It's like boop. And it's pointing to this node here, which holds a 1, and then a shared pointer to the next node. Okay, so technically there's a next thing, like this is pointing to a reference count of 1, because only one thing is pointing to this node right now. And then this holds a shared pointer to the next node, and it knows that, well, it's the only person pointing to that thing. There's a reference count of 1. And then this holds another shared pointer to the last node of the list, let's say, and let's see, another reference count of 1 here. And let's pretend that this is a shared pointer pointing nowhere. Okay, it's null. So first of all, the list will delete itself if first goes away. So this is just normal shared pointers right now. This is beautiful. Let me walk you through that example because it's fun to think about. So if first gets reclaimed, that means the thing that it's pointing to no longer has anybody pointing to it. So it's going to go and delete it. You see that? So first is gone. We know it's leaving, so we get rid of what it's pointing to because it was the only thing pointing to it. And then we'll do the same for this. Like, okay, we're going to get rid of this. That means the thing that it's pointing to, because it's about to leave, there's nothing pointing to this anymore. Okay, you see the chain of things that's about to happen? It's like, okay, now I got to get rid of this. And the thing that it's pointing to has nothing pointing to it, so I can get rid of that. And so on until the cycle is over, because we finally get to this one. It's like, okay, yeah, I got nothing left to do. Let's just get rid of me. Okay, so it'll delete the entire list once the first pointer goes away, which is awesome. Now, here's the problem. Actually, I think I can just copy this. No. There we go. Or not. Hey, I want to duplicate this slide, please. How about that? All right, so here's the issue now. With a circular linked list, you have the last node pointing to the first node. Okay, it just like goes around in a circle. So this is what it looks like. This is not null anymore. It is a pointer to the first node, which if you use shared pointers, it's going to mess things up. Okay, because once you do this, how many people are pointing to that first node? Well, let's see. There, they share first and the last thing is pointing to the first node. So this has a reference count of 2 now. So if first ever goes away, this is going to get bumped down to 1, and this list will never delete itself because this 3 is blocking this 1 from being deleted, which is blocking this 2 from being deleted, which is blocking the 3 from being deleted. You see that? So a shared pointer for the last node blocks the list from being automatically deleted. The solution is to use a weak pointer for this one, the one that ruins everything. Because you know, it's guaranteed that first is always going to exist, no matter what. If you're accessing this list at all, first must have existed, right? So that's the mindset. All right, we're almost there. Actually, it'd probably be easier to do that for this. And then break out the eraser here. So here's what we can do. Boop. A weak pointer doesn't have a reference count. It doesn't manipulate the reference count. This is just a weak pointer now for the very last node. And here's how we can do it. Just like this. So now, because this is a weak pointer, it doesn't increment the first's reference count, or this node's reference count, that is. Which means that when first goes away, it allows the rest of the list to go away, because the reference counts can go to 0. And that's what allows things to be deleted. Okay? So you just got to put a weak pointer at the last node. That's the idea. So that's fun. That's a cool example, I think. Maybe I'm going to try. Let's see if we can make this work. I'm going to, just in case we don't have enough time, I'm going to write up an example program and come back to it. Okay, let's do this. So I have made a node struct, and it has 2 different kinds of nexts, and we'll use just one in each. in each node, either we'll use the shared pointer or we'll use the weak pointer. And hopefully your program that's trying to iterate through the list will like use the next if it's there, or use the next week if it's not there. That's the idea. So, all right, a node has a data, a next, and a next week. We'll use one or the other of these two. And you can actually have destructors for nodes, and this is going to help us with explaining what I want to explain. And so every time a node gets deleted, its destructor gets called, and I'm going to output, hey, this node with data equals data has been destructed. Okay, so here's what I'm going to do. I'm going to make the list 1, 2, 3, 1, 2, 3, using make shared, and then I'm going to set their data just as normal, just pretend they're pointers, and set their nexts as well, just pretend they're pointers. So this is a circular linked list because of this last line. 3's next is 1. Okay, so I'm making it go all the way back. 3's next is 1. That's the idea. And I'm using shared pointers. So, oops. By doing that, here's what happens. If I only ever set the shared pointers, I hit enter, I get no output because the destructors never run. So none of this stuff is getting deleted because of the problem I was telling you earlier. But if I break that cycle by adding the last node, making it a weak pointer instead of a shared pointer, set the next weak part of the node instead, make it a weak pointer. You can convert a shared pointer to a weak pointer, no problem, using assignment, copy assignment. Now, everything gets destructed. Yeah? I hope that makes sense. The one node gets destructed first, then the second node, then the third node, in the order that I was talking about. Hopefully this convinces you that, oh man, these are super nice, and well, if you just had a normal linked list, you just use a bunch of shared pointers, and they would all just get deleted for you when you're done with them, like when you have no more pointers to them, no more shared pointers to them. Sounds beautiful. Hopefully you're as excited as I am about that. Feel free to use that for the rest of your life now. Now let's talk about the big 5. So we've been talking about the big 3 in this class so far. There are 2 more, and they involve moving, the concept of moving. So it is quite possible to move unique pointers around, even though you can't have them point to the same thing at once. So you can't copy construct or copy assign unique pointers, but you can what's known as move construct and move assign them. Okay, and what that does is it transfers the ownership of the pointer. So what it's going to do is, if I have a unique pointer that points to my thing on the heap, and I have another one, if I want to move UP into UP2, I eventually want this to happen. What it's going to do is it's going to break this pointer. It's going to make it null before I do that. That's what moving does for me. Okay? So by moving, like I'll use a dotted line, move of UP will do it. Okay, it'll break this link so that it's guaranteed that there's still only one thing pointing to this thing because it's a unique pointer. And then that means it's going to get rid of the original UP that pointed in the first place to this 42. So let's have an example of this. Let's move some unique pointers around. And let's go to code. Okay, so let's figure this out. Let's try to do this. Unique ptr move.cpp. How about that? All right. Oops. And so the first thing that I'm going to do is include memory, of course. And then I will make a unique pointer to an int up equals make unique, and we'll give it 42. Okay? So normally, make unique of int. Normally, you cannot do the following. You can't be like, okay, up2 equals up. That will not compile. Yeah? Watch it not compile. It's like, use of deleted function, that doesn't exist. You cannot copy assign, copy construct. So what you can do is move, okay? Move assign, move construct. So I say move up. And if I want to use move, that comes from utility. Whee. And what it does is it makes this thing movable. Oops. That, and then unique pointer move. There we go. So it works, it runs, and what happens to the original UP? Well, let's print it out then. Get the pointer that was there. It's going to transfer the pointer into UP2, which means it's going to empty out UP. So now it's null. You see that? That's the beauty of it. Okay, so let us go back and rejoice. So yeah, move just is defined in utility. It makes something movable. That's my first approximation to the real idea there. So utility has move, and it returns a R value reference to the thing that you give it, which is a very interesting idea. Okay, and we're going to talk about what that means to be an R value reference. And my cat is trying to bite me, and he has succeeded. Let me continue now. Okay, so the next step of the big five is to talk about what we can do with movement. Like, why would we want something more than constructor, destructor, copy constructor, and copy assignment operator? What else is there? Well, let's talk about unnecessary copying. So let's remake our favorite holder class that we know and love. You remember the big three for that? Well, I do. So I have gone and implemented all of this. So we got a holder class, it's got a constructor, a destructor, and it makes its thing on the heap. So we use new. It's got one member variable, it's called x, and we can get it using a getter, or we can do things to it. Copy construct it, copy assign it, watch out for that self-assignment, of course, and I've made a plus operator just as an example. Okay. So down here in main, I've got a few things happening. I've got made x and y, h1 is a copy constructed version of x, h2 is a copy constructed version of x plus y, and h3 is a copy constructed version of function returning holder. I guess I can be even more fancy and do the following. I could be like h3 of 0, and then h3 equals function returning holder, so that I can successfully also call the copy assignment operator. And so let me, I don't know, do that here. That's what I wanted. So now I've tried everything, which is fun. Okay. And what I'm about to say is that for these copy constructs and copy assignments, there are these, this one, and this one, two copy constructs and a copy assignment. Only h1 actually needs a deep copy, because x plus y and this function returning holder, they're returning like ephemeral things, okay? Operator plus and function returning holder return ephemeral holders. They're about to go away. So what's happening right now when I call the copy constructor on h2 with x plus y, I'm about to make h2, which has an x that's about to point to, what, 85? But x plus y is building up its own little holder that is, I don't know, it's called res or something, and it's got its own little x that's also, it's about to return, setting it equal to 85. And we are deep copying that over to here. Yeah? This is what we have right now. And this is very inefficient, because res, which is the result of x plus y, we're using it in the copy constructor, and then it goes away. I hope you see that. Res goes away. Okay? That goes away, that goes away. That's what we have. What we would like, can you see what would be nice about this situation? how we could save some unnecessary deep copies from happening? If we knew that res was about to go away, if we had control over knowing that, we could have just, before it got deleted, just hooked Rx into that heap memory. Yeah? So that before res went away, like, it went away, but the thing that it was pointing to did not. Yeah? So we didn't have to make an extra copy. That took extra time. We didn't need to do that. And you can think of like how bad that would be if we had a bunch of heap variables or a very long array inside of H2. Okay? So that's silly. Let's not do that. And the way that we can discover and steal stuff instead of copying it is through these things called R-value references, which are the types of things that are about to be destroyed. So operator plus and what's it called? Function returning holder both pass holder ampersands to the copy constructor / assignment operator. C++ can convert this to a holder, it's fine, it just copies it. But really it knows, C++ knows that those things are about to go away. So we can take advantage of that and steal their data. Let's do that. And the way we do it is through what's known as a move constructor and a move assignment operator. And we can also use move itself if we need to. So the idea is when you move something, you leave the other object in a state that is safe to be destroyed. Okay? We'll talk about what that means for holders, but just keep that in the back of your mind if you ever do this again. So the big 5 instead of the big 3 is when you also worry about the move constructor and the move assignment operator. So let me go pull up some documentation about this stuff. So here's some documentation. A move constructor looks like this. It takes the name of the class, it just has the same name, holder, and then 2 ampersands. That's what it looks like, okay? And it is everything else you imagine it to be. You can read all this information if you would like. There's a nice example that involves moving things, of course. But I'm going to give you an example for holders, and then move assignment operator is the same. Like it returns a pointer to a reference to the class itself, and its operator equals again, but it takes a new type. It takes holder ampersand. Okay, that's the idea. So it knows that we have an R-value reference, and it can do fancy things like steal its stuff. Okay, so let's go and implement this and see where it brings us. So we would like this to use the move constructor, and we'd like this to use the move assignment operator. Okay, so let's make this happen. So let's do move constructor and then move assignment. Here we go. So the move constructor, thank you past me for copying it right here, looks like this. And then move assignment operator looks like this. And here we go. So let's do it. So the move constructor looks like this. What it needs to do is bring in others, move / steal others data, and put it in ourselves. Okay, so we can do it like this. We can say x equals other.x. Okay, so that steals it. Steal x's stuff, steal other stuff. And then we need to put we need to put other into a state that is safe to be deleted. Because its destructor is about to get called. So right now, this is what we have. We have exactly this. We have H285 and res pointing like that. And we just stole res's stuff. And res is about to go away, remember. So we just stole res's stuff right here, like that. We did it just fine. But res is about to go away, and remember what res's destructor does. It deletes what it's pointing to. We don't want that to happen. We want this to stay around. So we can change res. We can make it point to null. And a nice trick about C++ is deleting null does nothing. Yay. So that's nice. If you wanted to be very pedantic, you can use move as well. So the line above is fine, but if you wanted to be extra pedantic, you could say and very expressive about what you're trying to do. You're about to steal stuff. You can say, people like to say, instead of this, they say move, even though it's unnecessary. In this particular case, it's unnecessary. Okay, so this will work. Steal others x, and then we need to put other into a state that's safe to be deleted, which means we should set others x now to be null pointer. Now it won't delete the thing that we just stole. Which is super nice. Okay, so the very last thing we need to worry about is the move assignment operator. And in most cases, remember that our value references mean you're using objects that are about to be destroyed. So you should really never be move assigning yourself. That should never happen, because that means you are about to be destroyed. So if the user accidentally used move for this, they made a huge mistake. The internet is quite conflicted about whether you need to check for this. I say, why not? So if this is equal to the address of other, return this, otherwise do our stuff. So we do essentially the same stuff. We say x equals move. Oh, I'm sorry. First we need to delete ourselves. We're about to replace ourselves. So delete x. Then we need to set x to the other's data, steal it. Again, for pointers, you don't actually need move, but sometimes you do for other bigger types. And then we say other.x again equals null pointer. And finally, we say return star this, as one does normally. Okay, so that's it. That's the move assignment operator. And what it's doing is, if I give you the example, it's going to return function returning holder. So it's like I had a ret, or I had a res or something, and that was assigned to h3. H3 was originally pointing to 0, and then the res from that other function was pointing to 44, I think. And so what we just did is we stole, well, we deleted ourselves because we were about to be copy assigned. Then we stole res's stuff. Boop. We didn't make a deep copy because we didn't need to. Res is about to go away. And then we got rid of res. We allowed it to destruct itself properly by setting its pointer to not there anymore, but to just null. Okay? So it's like pointing nowhere. And then res can be safely destructed. Same with this res up here. Forgot to draw that. So we stole its data. We didn't have to deep copy it, so it saved us work. Super nice. Okay. that, in theory, should work, and I can now print when we're using it. See out. About to move assign a holder with x equal to, or star x equal to, other dot get x. And I can just say x and star it. It doesn't really matter. And so that's for move assignment. Now I can say move construct as well. And hopefully it'll work. We'll find out. Let's go down here. So, moment of truth. We successfully move assign the holder, and that works as usual. But this x plus y is not quite working the way we want it to. And the reason for that is because technically C++ is a bit smarter than us, and it doesn't actually use the copy constructor or the move constructor here, but we can just explicitly make it use the move constructor by moving x plus y. Unnecessary, though, just to prove a point. Oops. This will work now. Why not? So that is the move constructor and the move assignment operator in a nutshell. Oops. And yeah, that's all I wanted to say there. Now just a few last examples, really quick, and you're out of here. So I'd like to teach you some cool standard library functions now. I don't think I have time for all of them, but let me at least teach you like for each, and then I could just at least talk about transform and count if. So for each lives an algorithm, boop, 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 and where is it? What it does is it calls a function. Like you can pass a function along, and it calls the function on every element in the range between two iterators. So let me show you this. So I'm going to include vector and algorithm. Dun, dun, dun. And what I'll do is I'll make a vector int v equals 1, 2, 3, and then I'll say for each element between v.begin and v.end, please call the function print v, or print int. It takes an int, and it just couts that one int. So please call this function for every element of v. And I can see, I hope you can see that this is going to help you quite a bit. So let's compile and run this. These kinds of little algorithms are super nice. It just prints 1, 2, 3, and it's probably the first time you've seen it, but I'm using a function as an argument to another function. Magic. So that's for each. And now transform and countif are very similar. I've got to look them up. So transform just applies a function to everywhere. So like you can increase everybody in the vector by 1 by making a function called like void inc int x, just return x plus 1. So it'll do this and reset everything inside of v. Be like transform by inc and put everything back in the vector v at the beginning. You have to add that again for no good reason. Oops, and this is called inc. And if we print it back out, we should have 2, 3, 4. No. Oh, sorry, it needs to return an int. Now we have 2, 3, 4. I promised I was only going to do 4 each, sorry. And then count if is very similar. You give it another function, and it counts whether or not, counts how many elements satisfy that function. That returns a Boolean. So count how many things are odd, for example. That's all nice. That's algorithm. And it's kind of silly to have to make a brand new function to make things work. So you use something called lambdas. Lambdas in C++ define anonymous functions, as in functions without a name. So instead of all of this, I could have said for each v.begin, v.end. Now, pay attention, I go 2 brackets and int x parameter, then a body, cout x and l. That is what a lambda looks like. Okay? This is a function with no name that takes one int argument, with no name that takes an int and couts that int. Super nice. You don't have to define an extra function if you're only going to use it in one place. So that'll do the same exact thing, but we didn't give a name to this function. It's called a lambda. We're defining a function in line, which is so weird. This rabbit hole goes really deep, and I'm sorry I don't have enough time to talk about it in depth, but please yell at me. Come to office hours. I'd be glad to tell you more about these lambdas. Finally, a few more topics. I just don't want you to forget about Valgrind, first of all. I don't think I have time for the example, but just remember that if something goes wrong, you can always say Valgrind leak check equals full, my program, and it checks whether or not you have done silly things, like you have leaked memory, you have written past the end of something, like it knew that the vector was a certain length, and you accidentally wrote past the end of that. It will tell you. And at the very end, it'll say things for memory leaks like definitely lost and probably lost. And I just want to make it clear that in this class, either case, you most likely definitely messed up. So probably lost is still, from the perspective of this class, from the things that you know how to do, it means that you definitely lost these, a pointer to somewhere. You're doing weird things. So just remember Valgrind leak check equals full, and then run your program. It's super nice. Okay, the final thing that I want to talk about is SSH and SCP. And we're going to practice using the class server. So if you've never used this before, now's the time to learn. SSH stands for Secure Shell, and SCP stands for Secure Copy. So to SSH, you log into another computer. In each case, you'll be on the server. You're plopped initially into your home folder. That's you. That's where your stuff lives. And let me show you how to use it. You say SSH, your username, at, well, it's going to be server.lawtonsclass.com, but it could be any computer here. It's like an email, but it's like your username. And that's how you get a terminal on another computer. And this is what's happening under the hood when I'm submitting your stuff. When you're submitting your code to the class server, this is exactly what's happening. So you can say SSH test. So your username, server.lawtonsclass.com. You hit enter, and now you are in another computer. This is not you anymore. This is not your local machine. This is not VirtualBox. So your current working directory is in your home folder. You've got some stuff there potentially. And you can actually do your labs here. You can edit files. And notice that this file that I'm about to edit, like, hi mom, it exists here. It's not on my local machine. So if I go to my home folder here, cat foo.txt, it's like, no, that doesn't exist. This is on another machine right now. And you can use Vim, you can do all this stuff just remotely. So that's super fun. That's SSH. Do consider using it. You're connecting to another computer. And then finally, say you want to transfer files between these things. SCP, you say the thing that you want to transfer, then a colon. If you want to transfer from your other computer, you use the other computer first. Be like, foo.txt, transfer that, please, to my current directory. Let me remove the hyperlink because it's looking silly. So SCP, what you want to transfer, and then where you want it to be transferred to. It's just like using the cp command, but across computers. So the file name for a remote file starts with username at server address.com, and then a colon, and then path to file. And then the rest for your local computer is the same. So if I want to get the foo.txt onto my local machine, I can do scp, and dot stands for my current directory. So I can say this, copy the file that exists on the home folder of /foo.txt for the user test 8675309 at this computer, copy that file to my current working directory, log in, and bam, it copies it. So I can say cat foo, and it's now on my local machine. Okay, fun stuff. Please play around with the server if you feel like it. But that is everything that I wanted to say today. So some quick exercises, and then let's get you out of here. So I would really think it's a good idea if you tried to convert one of your previous labs, if you feel up to it, like on lists, on trees, to use smart pointers, so like shared pointers, and then suddenly you don't need the big three anymore because everything's going to be deleted for you. It's beautiful. And then maybe consider doing your final lab on the server if you feel like it. So I think that's everything that I wanted to say. These slides were a huge potpourri of topics. I'm not really going to test you on them. So this was more for your own education and to get you ready for the next classes that you'll take. Okay, so I hope you enjoyed this fancy C++, and I will see you later.